Okay, so we're going to talk about the exponential function as a mapping now. So remember, e to the z is e to the x plus iy, which is really e to the x cosine y plus I e to the x sine y. And we saw already that this is 2 pi I periodic. That is, every 2 pi increase in the imaginary part causes repetition of the exponential function. So in other words, if we were to, it's convention to mark the imaginary part at pi intervals. So here is a 2 pi interval distance in imaginary parts. So every time we have one of these chunks, whatever e to the z does to this part, it's going to do to the next chunk. So here, let me do a chunk here, and suppose this goes up to 3 pi. Let me do a chunk here. The output of a point of this, say, red point here is going to be the exact same as the output of that point plus 2 pi I. So that is e to the z plus 2 pi I is e to the z. All right, so it's 2 pi I periodic, and so to figure out what it does to all of the complex plane, it's enough to understand what it does to a slice with the understanding that it sends each of these 2 pi sort of horizontal strips that have width 2 pi to the same location. And so we'll often use just the one that's closest to the origin. So let me get rid of this and make it dashed. So we're often going to use this guy. And this one here is called the fundamental region for e to the z. Fundamental region. We encountered these before when we were looking at principal values. And e to the z, again, since it's not 1 to 1, it's many to 1. We look at a fundamental region so that we can construct the inverse function, which is the log function. But nevertheless, here's our fundamental region, and we want to know what it does to things in that fundamental region. So first, we're going to talk about horizontal lines. All right, so let's draw our region one more time. So we're going to mark it pi, we're going to mark negative pi, and we include pi, but we exclude negative pi, like with the principal argument. We're going to look at what, I'm not going to fill it in because we're going to draw horizontal lines here. We want to know what happens to horizontal lines. So let's mark some values here. Let's mark maybe, I don't know, 1, 2, -3. And we're going to draw horizontal lines with constant real part at 1, 2, and at -3. All right, let's call this L1, L2, L3. So the question is, what does it do to those lines? Well, L1 is a collection of all 1 plus yi, where y varies between negative pi and pi. So when we exponentiate this, this tells us then that when we exponentiate 1 plus yi, we're going to get e to the 1 cosine y plus e to the 1 sine yi, where y varies between negative pi and pi. And if you think about that for a second, that's a circle of radius e, and it's the full circle, because we have all of the angles, all the way from negative pi to pi. So the image of L1, if we mark E here, put it in green, the image of L1 is a circle of radius E centered at the origin. Now what's going to happen when we do L2, so this is image of L1. What happens when we do L2? Well, the only thing that's going to change here is the real part's going to go from a 1 to a 2. So it's going to go from e to the 1 to e squared. So e squared is much bigger than this, but I haven't given myself enough space. If we mark e squared, we're going to get a circle of radius e squared. Okay, so again, it's not the picture, but give me a break here. And when we go to -3, what's going to happen? Well, we're going to get a circle of radius e to the -3. That's a very small radius. So here's image of L2, and here's image of L3. So if you think about what's happening here, with our negative values, we're going to get circles of arbitrarily small radius. We're never going to get to the origin because the exponential function is never 0, but we're going to get really close to 0, homing in with circles of smaller and smaller radius. And when the real part's very large, we get circles of very large radius. And there's a critical point. There's a critical, well, not critical in the calculus sense, but there's a threshold point here, namely that sliver of the imaginary axis where the real part's 0. Well, if the real part's 0, we're going to have an e to the 0, which is a 1. So that special guy is going to get sent to the unit circle. This is unit circle. So anyways, what it sends horizontal lines to are circles that sweep out the plane minus the origin in successively larger and larger radius as our real part gets bigger and bigger, and smaller radius as our real part gets more and more negative. So that's what happens to horizontal lines. Let's see what happens to vertical lines. Right, so again, we're going to draw our fundamental region. Oh shoot, did I mess up the words? I messed up the words. Sorry, I always confuse horizontal and vertical. My bad. All right, now we're going to do horizontal lines. Sorry. All right, so let's draw our fundamental region again in green. All right, and now we're going to do horizontal lines. I'm going to get it correctly here. So let's mark it, I don't know, here at pi halves. Let's mark it 0. Let's mark it negative pi halves. And let's look at what happens to this one first. All right, so what do points on this guy look like? Well, your imaginary part's constantly pi halves. So it looks like x plus I pi halves, or again, it's constant pi halves. And x is allowed to be any real number, right? Because we go infinitely to the left and to the right. So when we exponentiate this, we get e to the x plus I pi halves, which is e to the x cosine pi halves plus I e to the x sine pi halves, which cosine pi halves, sine pi halves, that tells us that we're going to have an argument of pi halves. And it tells us also, since we have an e to the x there, we trace out sort of everything with an argument of pi halves. So we're never going to get 0, of course, but that is going to go to this ray. And how is it going to go to that ray? Well, when your x is very big, you're very big. So so as x increases, we go that way. And when x is very negative, so as we're trailing off to sort of negative infinity in our real part, it wants to get close to 0, but it never quite reaches 0. All right, let's try another horizontal line. Let me use different colors for this example. Let's try this one at 0. Where does that go? Well, that has an argument of 0, because instead of a pi halves being on the imaginary part, we're going to have a 0. So that's going to get sent here to all points that have an argument of 0. And let's do negative pi halves now. Let's see. Maybe do orange. So that's going to, again, our imaginary part's negative pi halves, so we're going to get sent to all points that have argument of negative pi halves. And let's just mark one more case here just to see in general. If we have a theta that we're marking our horizontal line at, then it gets sent to all points that have an argument of theta. All right, So what we learned here is that vertical lines transform to circles. And not only do they do that, but the negative real part guys are sent to circles of radius less than 1, and it's decreasing as you go more and more negative. And the positive real part guys get sent to circles of radius larger than 1. And they get bigger and bigger depending on how far you go out. And in general, the radius is going to be e to the real part. We saw. Now we just saw horizontal lines get transformed to rays, where it's a ray with argument the imaginary part. All right, and so we have an understanding now of what the exponential function does to horizontal and vertical lines.